This video is about local maximum and minimum values of a function. For our notes, we'll start with just a couple of definitions. And first, we'll say the function value f of a is a local maximum value of function f if f of a is greater than or equal to f of x when x is near a. For all x in an open interval containing a. Now, there's a lot to this definition, so let's try to unpack it a little bit before we see an example. First of all, let's recall that using function notation, we could see a point on a graph written as a comma f of a, where a is like the x value and f of a is like the y value. So let's just keep this in mind. These definitions tell us that f of a, which is really the y value, that is the local maximum, or as we'll see, minimum value. The x value, in other words, the a, where it occurs, simply tells you where it occurs. So we could say occurs at a. So a is where on the axis the min or max occurs, but the actual min or max value is the y value, the f of a. And so, of course, in the next definition, it's for a local minimum. In this case, f of a is less than or equal to all other values near it. And so we'll take a look at a graph, a picture of a graph that will help put some examples to this definition. This first example wants us to list all local maxima and minima. And you'll see those words ending in a. That actually means that they are plural. Minima is plural for minimum. We don't say minimums, we say minima. Same thing with maxima. And then we also want to list the intervals over which the function is increasing or decreasing. So we'll start by just looking at this picture, which is a curvy graph that starts low to the left, and then it kind of curves up and down and up and down like a roller coaster, and then ends up going up to the right. So starting, down to the left in quadrant 3, and then up to the right in quadrant 1. Anywhere we see a peak or a hilltop, you could say, of this graph, we could look for that to be the place of a local maximum. And so you can see there's a peak or a hilltop apparently where the x value would be -2. We'll put a point at the hilltop there. There's another hilltop where x is 1. And those would be the places of local maximums or maxima. Now, we know that it's local because it's just the max within a certain place. For example, in quadrant 2, if you take a look at where the function is -2, we have a hilltop up here. It seems like that function output value seems to be 3. So at the point -2, 3, it seems like that's the top or the peak of the graph there. But it's not ultimately the highest place. If you look over to the right side where the arrow is going up, that graph's going to keep going up to the right, meaning it's going to go much higher than this hilltop we observe, which means it's a local maximum. That's exactly why we say local, because locally it's the highest, but not ultimately or globally is it the highest. We want to be able to list all these places. So let's see if we can start by listing any local max. We just found one. Now recall from our definitions that it's the y value that's the actual max value. The x value of the point tells you where it occurs, but it's the y value that's the max. So the max would be, in this case, or that first example, 3. In the second peak or hilltop we observe where x is 1, of course that's the point 1, 2. So the y value of that point, being 2, would be our also local maximum value. And since those are the only hilltops or peaks that occur within the picture, right, we're not including the arrow because that's going up forever, then only those two places will represent our maximums. We can think along the same lines to observe where any mins or minimum values may occur, and we'll look this time for some valleys. It does appear that there is a valley at the point -1, 0. But then another one in quadrant 4 at the point 2 comma negative 1. And so to find the minima or the minimum values of our function locally, we'll look at those y values and say that 0 and negative 1, representing the y values of those 2 points, count as our local minima. Now, knowing where the extrema, or maxima and minima, occur will help us accomplish the second task, which is to list the intervals over which the function is increasing or decreasing. You see, at a local max or minimum value, the increasing or decreasing we would expect to be changing, so we can look around those to find it. In other words, we'll start by looking for places where the function is increasing. It looks like, now remember we're thinking left to right here. If you start all the way to the left, which has the graph going downward forever, that means it's increasing anywhere over there. So we'll start at negative infinity. And it seems to be increasing as we ride up this graph all the way to the first peak, which we've used as a local max. And so the x value of that peak, which is negative 2, is where we could say the graph is increasing until. Right? Until x is negative 2, the graph is rising up, 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 and then it hits the peak at negative, well, the peak is when x is negative 2. The actual peak value is 3, the y value there. But it hits that peak when x is negative 2. So it's increasing on that interval. Then it starts to wind down, so we'll look for the next interval to start at the next valley, which would be when x is negative 1. And then it seems to increase or rise until the next peak, which is when x is 1. And then it dips down again. And then it does seem to increase one more time, starting at that second valley, which is when x is 2. And then it seems to increase or rise forever thereafter, thanks to the arrow. So we'll say 2 to infinity. So it does seem to be that there are 3 intervals over which this graph is increasing. And notice we're just separating the intervals by commas. We're not using any union symbol here, just different separate intervals of increasing. We can do the same kind of process to find out where the graph is decreasing. Notice this should not be the same intervals where it's increasing. It's only doing one or the other. But we can use the graph and its labels to figure out the other missing decreasing pieces. It looks like the first piece occurs between the first peak and the first valley. So that would be between negative 2, when x is negative 2, and when x is negative 1. Then it's increasing, so we pause, but go to a next decreasing interval, which looks to be between that second peak and valley. So between when x is 1 and when x is 2. And if we consider decreasing or increasing to be a left to right motion, it does not occur that there are any other places of decreasing from left to right in this graph, which means we've covered all the intervals of increasing or decreasing that we need, which are all related to the max and min. So notice, just as an observation at the end here, the max and min values, these are y values, but then where the interval boundaries were, these are all x values. So it's good to observe that and understand what we're using when we describe all the pieces of this graph. Let's try a second example where this time we're going to use a graphing calculator to find a local extrema for the following function. And we're going to, of course, list the intervals over which it's increasing or decreasing like we did with the previous example. But this time, we're not given the picture of the graph of the function. We're just given its definition. So we want to turn to our graphing calculator and take a look at it. In our graphing calculator, we'll go to the equation editor by hitting the y equals button in the top left corner. Clear out any equations we might already have there from previous use. And then in the first spot, we're going to type in this function as we see it. So we have x to the 5th minus 8x cubed plus 20x. Now, of course, we need to find the local min or max values in this function, and to do so with the calculator, we're actually going to want to look at a picture of it. So let's just start by doing zoom and then maybe 6 for a nice standard zoomed out window. And let's see if that's going to display enough of our function. Okay, you can tell that it seems the graph is cut off both above and below. We're going to want to adjust our window so that we can see clearly where those peaks or valleys may be in the graph. We'll do this by adjusting our window. It looks like we need to move it up and down a little bit. So let's hit the window key, and for the y min, instead of -10, why don't we try -15 just to see if that's enough. For the y max, to move the window up, we'll try 15. Let's just take a look and see if it allows us to see the peaks and valleys more clearly. And indeed it does look to be that way. Now, those actual x values where the peaks occur will help us determine where the local maxes are. The x values where the valleys occur will tell us where the local minimum values are. And the calculator actually will tell us exactly where those are. Well, at least it will approximate them. Here's how. Once we can actually see the peaks and valleys in the picture, after adjusting our window, we want to hit second and then the calc menu. And this time, there are two options that we've maybe seen in passing before, but now we want to use. We'll start with the first one, option 3, which says minimum. I'll hit enter on that option, and then we have to just pick on one at a time. In the left side of our graph, in quadrant 3, there seems to be a zigzag that includes both a max and a minimum value. I want to spot that minimum first, and do so by, first of all, noticing the question in the bottom left corner, which asks for a left bound. Okay, what that means is I want to move the cursor, which I can do by hitting the left and right arrows. You'll observe the cursor moving. I want to move it until the cursor is clearly, but not too far from, the left side of this valley point that we see. So as long as I'm clearly to the left of it, I'll hit enter. And notice now the question changes, it wants a right bound. So now I need to go clearly to the right, which means, yes, I need to dip that back down and then start coming back up and hit enter when I'm somewhere to the right of it, but not too far away. And then it wants a guess, so I'll move the cursor maybe back to the left a little bit so I hit what seems to be maybe near the bottom of that valley, and then hit enter there. It thinks for a second and spits out what it approximates as the actual coordinates of that minimum value. So the coordinates given to us by the calculator, rounded to the nearest hundredth, would be an x-coordinate of -1.04 and a y-coordinate of -13.02. But let's recall, this is where the minimum occurs. The minimum is at this point. The actual min value is really only the y value. So we'll say our min value will be, at least for this first one, -13.02. Now remember, that wasn't the only valley within this function, so we're going to go back and list another one or find another one as well. We'll have to start over by hitting second calc again, and then again select minimum. And this time we're going to look for the other minimum, which was in quadrant 1, somewhere around where x is 1 or 2, somewhere close to that. So we're going to scroll over there and answer the exact same question. We want a left bound. I want to get close to that min, but not too close, so that I know I'm clearly to the left. Hit enter. Then it's going to ask for a right bound, so scroll past it to the right and hit enter there. And then for my guess, I want to scroll back to the bottom of where that graph seems to be. Hit enter. It'll think and give us that minimum value. The second minimum point occurs at the second value, which is when x is 1.93 and y is 7.87. Remember, the y value is the actual min. So instead of, or along with -13.02 from the first one, we'll get also 7.87 as our second minimum value. If you look back at the picture, it does not appear that there may be another valley in this graph. Now, to be absolutely sure, we could zoom out a little bit to make sure. Let's try that. Zoom, and then option 3 is zoom out. So we hit 3 and then enter. Sometimes the graph can get too distorted though in this way, so you might have to kind of zoom around just to be sure, but it does appear that there aren't any more wiggles, at least in what we can see from the graph from that point of view. So for now, we're good with that. We'll just zoom back in with a zoom 6 so we can see at least a closer version of the graph we've already worked with. Let's go back to our viewing window where we can see the peaks and valleys of our graph. We did that by adjusting the window button originally. I think we used -15 and +15 for the y min and max. so that we can see the wiggles easily. We now want to look for the maxes, which are the peaks of these little curves here in the graph. So let's go ahead and do so by hitting second and then the calc button. We want to use this time maximum, number 4 option. And we'll go through the exact same process. We want left bound, right bound, and then a guess for each of these. Now, if we look back at our list of points at which these min and max values occur, you'll start to observe some symmetry, and that's because this is a nice, symmetric polynomial type graph. We'll learn more about symmetry later on in this course, but for now what I mean is notice there's a 7.87 and a negative 7.87. There's a negative 13.02 and a positive 13.02. That doesn't always happen, but if a graph is symmetric in a certain way, then you will see those repetitions. So we'll recall that our max value is actually the y-coordinates of our points here that occur at the peaks of this graph. And so negative 7.87 and 13.02 would be our max values for this function. Now that we have the local maxima and minima listed, let's go ahead and see if we can understand from that and the picture where this function might be increasing and or decreasing. If we take a look at the picture, we'll notice that it's increasing all the way to the left, but then until it hits the first peak. And we know exactly where that first peak is. So we can see it's increasing from negative infinity to negative 1.93, which is the place, the x value, where that first peak occurs. But then it's also increasing in other places. As we look back at the graph, you'll notice between the first valley and the second peak would be a spot of increasing. The first valley was the first minimum. That occurred when x was negative 1.04, as we can see from above. And then the second peak, which is where this increasing seems to level off or max out, would be when x is 1.04, as seen from the x value of our second max point. Then it does appear that the graph continues to increase after the second valley. So anything from that on to infinity should also be increasing. Let's recall where that occurred. The second valley occurred when x was at 1.93. So we'll say 1.93 comma infinity to represent everything after that. For places of decreasing, remember we're only moving left to right when we consider this. And it seems like it's only decreasing in that way from the first peak to the first valley, which would be negative 1.93 for the x, to the first valley, which is at negative 1.04, and then also from the second peak to the second valley. So that'd be 1.04 for that second peak. The second valley would be the 1.93. Again, we're just referring to all these x values for the locations of the mins and maxes because that's where the direction changes, either from increasing to decreasing or the other way. Based on the picture and what we're looking at, it does not appear that the graph decreases anywhere else, which means that should do it for intervals of increasing and decreasing.